Hi everybody, I'm Steve. That's loud. Um, this talk is called Compiler Errors in rustc, a UX Perspective. I just got off the plane from New York this morning, so I'm going to try to keep it a little energy high because I'm pretty exhausted. But this talk we're going to talk about compiler errors in rustc. Why would I be talking about this? I am on the Rust team. I work at Mozilla on Rust. And my job is mostly documentation, and so it's usually not inventing stuff myself, but taking the things that are like the rest of our fantastic people do and figuring out how to explain them to people who are not part of that. And so I actually pitched this talk to Øredev because I wanted to learn more about this topic, and so I learned more about it, and I'm now here to like share with you what all this work other people did. So this is not the work that I do personally, but yeah. I want to share how it works. The other funny thing was this initial screenshot. So we use Discord for developing Rust these days. And so someone ran cargo test, and one of these tests failed, and it said error, test failed to rerun, pass, test spanned, which would like rerun just the test that failed. And they said, wow, these errors are really good. Thanks, cargo team. And even though I'm not going to talk about cargo errors a lot, I still put this as the front thing because it just serendipitously happened as I was making this test, or making this talk. And so this is sort of about rustc errors, but we also carry it through to like the rest of the project, like other tools that we produce. We care a lot about errors as well. I used our documentation generation tool to make this talk, so I kind of got a little overview of what we're going to talk about here on the side. I'm going to shove that away in a second, but basically we're going to talk about the why of error messages and making them good, and then how those things actually happen. And the how is obviously a little more complicated than the why. Okay. Why should you care about error messages in the first place? In any open source project, there's like a lot of different stuff to do, and there's never enough people to actually do it. So you have to pick and choose what you actually spend your time on. And so why should you spend time on compiler errors? For Rust, one of the primary reasons that we decided to work on compiler errors is that Rust is not necessarily the easiest language to learn. And one of the ways that you can help reduce that learning curve is by giving people excellent errors. I'm not going to read this giant wall of text to you, but this is a screenshot of our discourse forum where someone was like, hey, is it possible that maybe Rust is like too hard and that's going to like harm adoption? And this post was from June of 2016. So, you know, we've done a lot of work since then, but like this is kind of the core reason why we decided to invest in this kind of thing. And you know, even tools that are like more easy to use can still benefit from this as well, but we really see this as part of like the process of learning Rust is you're going to see a lot of error messages, and those error messages should actually be helpful because you're already frustrated enough that you're getting a bunch of error messages. Why not, you know, at least have them be reasonably, you know, good ones? There's kind of a joke in the Rust world that like the answer to every single question about Rust is a compiler error. I'm assuming you know maybe a little bit about Rust since you came to this talk, but if you don't, we have a very strict compiler that checks a whole lot of stuff, and so most of your time will be seeing like your program not compile instead of actually compile. And I like to think of this more as sort of like TDD, you know, where your tests fail and fail and fail until they pass. So we just compile, fail, and fail, and fail until things compile, and then you get to do the tests that fail and fail until they pass. But you know, this is also just part of programming. I don't want to get off into the other topics about that stuff, but it's just part of life as a programmer. Another reason why error messages matter in general is not just like with Rust being hard to learn, but languages actually compete on user experience. And this is something I don't think we've appreciated as much in the past, but we've started to. I'm including some really old examples from GCC and Clang because one of the things, these are both C compilers, not Rust compilers. Problem is still the same. One of the things when Clang came on the scene that differentiated it from GCC was that it had significantly better error messages, and that made GCC actually catch up and work on their error messages and make them better. So both of these are like really old examples. I basically like remembered this happening and was like Googling for really old blog posts. So I put a link, these slides are on my GitHub so you can like see exactly what it is, but I want to make a point. These are not like today's error messages. These are like I Googled for old error message output. So here, this C program, there's sort of these two problems. One, there's no semicolon after this printf statement, and then there's no semicolon after this return. And so what GCC 7 series did back in the day was it would say, hey, you need a semicolon before return. And that's like technically true from a grammar perspective, but it's not what you would actually write, and it like seems a little confusing. Like, why would you start this line off with a, and it totally misses the return 0, needs a semicolon as well afterwards because of reasons I don't know. This was the MSVC compiler from roughly the same time period, and it gets stuff a little bit better. It's like, hey, it still says you're missing one before the return, but it also says you're missing one before the end curly brace. So it's getting the second one, but it's still not like that fantastic. Whereas Clang, I messed up this indentation, I realized when I copied and pasted this from the blog post, so it actually would point to like the end of the statement, but it says, hey, you need a semicolon after this printf, and you need one after this return. So this is like significantly better than the other two, and they all now give reasonable messages, but this is kind of like the, sort of the reason, like this helps you get past your problem in an actual reasonable way, as opposed to kind of like reading the tea leaves of what the compiler was thinking about, and you have to like go through what it is in your head, and it's like a lot of work. And overall, I think one of the other things about error messages in any project, not just compilers, is that, thanks to people paying attention to this stuff, the standards of what people expect is significantly higher than they were in the old days. And so there's this like blog post, Compiler Errors for Humans, Rethinking the Terminal UX in Elm 015 from a long time ago, where Evan from Elm basically said, like, what happens when we accept that there's a problem with error messages and we try to do better? I learned you can make a shockingly big difference by just thinking about the user experience at all. And so Elm pioneered these errors. This is, again, back from the time. This is from that blog post. Elm is much farther now. But like here, we have an array down here, this user picks, and it's got 2 images and then this string, which is theoretically linking to an image, but that's not actually like correctly typed because you need the list to have the same type in each time. And so Elm's error message here says, the third element of this list is an unexpected type of value. They should all be the same type so we can iterate over them without running into unexpected things. I am seeing conflict between HTML and string. So this is like above and beyond, like it's not only giving you like where the error happened with like good squigglies, but it's also explaining like why that matters, like why does this array need to have all of the same type in the first place, and it's also telling you the like conflict that happens here. And so even this blog post acknowledges that this is not perfect, but like there's like a significant difference between errors of sort of this style and the kind of like compilation failed, nothing happens. There used to be this contest for what is the smallest C++ source file that you can get that generates the largest amount of compiler errors. And the winner was something like a 65-byte file that generated 4 gigabytes of error output from the compiler. So, this stuff like does actually matter and affect your, your day-to-day. And in general, like your users will love you if you put time into this thing that they run into. There's some random quotes from people said, like it's pretty amazing and detailed how helpful Rust error messages are. Note, I'm actually going to show how bad that error is that they're talking about later. The person that said that was pointing out an error message that we now consider to be a bad one. Rust is more complicated because it has more stuff, but people put a lot of effort into making the error messages readable, and it really shows, and those make learning Rust much nicer. And we've been the most loved programming language on the Stack Overflow survey for a while, and that's kind of a dumb metric, but I'm putting it up on the slide because it looks good anyway. But I just want to acknowledge that like the most loved is like the people who are using it still want to use it in the future. So as a relatively smaller language, we have less people, so it's much easier to get a higher percentage of people that love it. But whatever, 3 years in a row, I'll take it anyway. Okay, so let's look at that amazing detailed error message that first person loved. It's this one on the top. So we also, like, in Rust, we have a lot of work to do, and we've been working on improving these things. And so I also don't want to like say that, if you're working on a project, you should copy exactly what we're doing. But like I think there's a lot more that we can do. So this one they loved is this error cannot borrow v is mutable because it's also borrowed as immutable. Note previous borrow occurs here, the immutable borrow is here, previous borrow ends there. So this is like relatively detailed. The point of this error message in Rust is you can only have things like you have immutable and mutable references, and if you have a mutable reference to something, you cannot have an immutable reference to something. So you get like as many immutable references or one mutable reference. So here, I should have actually put the code on the slide, but it's in the bottom one, so you'll see it in a second. But the point is we're trying to like take a reference to the first element of an array and then push onto that array, which would cause invalidation, blah, blah, blah. This is not a talk about actual Rust code. But the point is that like we had all these like file name line stuff on the end, and that's basically because like Vim and Emacs use that information to give nice errors in the actual output that they have. This is kind of like a semi-standard format sort of thing. But for humans, it's like really ultimately redundant and sort of silly. So we ended up giving that up. And so that error message today ends up looking like this instead. So it's like closer to the Elm style, but not also totally the same. So can't borrow v is mutable because it's also borrowed as immutable. And then like this line of code is where the immutable thing happens. That line of code is where the mutable thing happens. And the immutable borrow ends at the end of the scope. And so this has like contextual line numbers. It's actually showing your code a little bit better. It's like pointing out the specific points in the line. And so this is kind of like a little bit better of an error output format. And we still managed to save the like Vim and Emacs understanding those line numbers things by detecting if you're not running it in a terminal and spitting out that output, you know, if you're not, and some other ways to like, I'll talk about options for formatting errors a little bit later, but like you don't have to give up the benefits of that stuff in order to have something that's actually better for humans. Okay, so that was all of the sort of like why background stuff. I wanted to cover that like kind of quickly before we got into the rest of it. So how does the Rust compiler actually like do this stuff? In order to understand how the compiler does this, you need to sort of understand how the compiler works in general. And so I'm going to give you an overview of like how the compiler operates, and then that will show you where the problems are for like generating good error messages. So we're going to talk about the compiler in terms of these passes that happen. Technically, we're in the middle of a really big refactoring that is moving from compiler passes to compiler queries, which is not sort of important, and you can still think of it in this pass term because even though we're working on that, it's not done yet, and like the real world is sloppy. So I'm giving you the kind of like easy overview, the way it used to work, and if you care about those details, we can talk about it later, like why that's changing. But like fundamentally, classically speaking, the compiler takes your source code and it produces what's called an AST, or an abstract syntax tree, and then it goes from the AST and turns that into here, which is a high-level internal representation, and it takes that here and turns that into mir, which is the mid-level internal representation, and it takes that mir and produces LLVMIR, which is LLVM's internal representation, and then LLVM takes that and produces the final output binary. So there's kind of these steps, and these steps are called lowering, so you like lower the AST to here and you lower here to mir, because at each step the language that gets represented is actually simpler than the previous one. And I'm going to explain what that sort of means in a minute, but these are kind of the like major phases that happen sort of in the compiler. And there's reasons, and we're going to get a little bit into those reasons for each one of them. Like a lot of people are like, why do you need 5 different internal representations? It turns out that like having more can actually be faster, which is like weird, but that's totally separate. But we're going to talk about how this particular bit of code, so we have a public function called +1 that takes a 32-bit number and returns a 32-bit number, and it just adds 1 to the number you pass in. We're going to like talk about how this goes from this source code that you write the whole way to LLVMIR, and then just ignore. I'm not going to show you the binary output because that's sort of silly. And we're going to talk about how errors like would be presented when doing this stuff. Okay, so the AST. Fundamentally, like an AST is taking your code, but it's turning it into a data structure that the compiler can manipulate. So there's this thing that you can run, -z AST-JSON, and it will spit out your AST in an actual JSON format. I'm actually not sure why it produces JSON here. It's the only one of these steps that produces JSON. I think it's because it's like somebody wrote it that way, and so it's just fine. Not a lot actually happens in the AST, but this is a small snippet of the AST that the rustc compiler would actually generate for just the x+1 part of that previous whole shenanigans. So here you can see like statements as an array, and then inside that we have like this binary operation This is variant binary, and then it's an add node, so like the compiler knows we're adding two numbers together. And then inside of it, it has this like path, and that path has a segment with an ident of x. So that's like, I've shown you the like x plus part of that whole function takes up all this garbage. So I don't like get into all the details, but like the point is that this is like taking your source code and turning it into something that the compiler can actually manipulate. And there's like parsing and lexing and some other steps that happen in there, but we're just kind of ignoring that. It takes your source code and turns it into this AST. This is not super nice to work with for a number of different reasons though. And so the AST ends up being lowered into this here, or like high level representation. And the primary two things that happen in between these steps are like macros get expanded out and all the names get resolved into like their long form names. So when you type like a regular function, you know, you may have imported that function earlier. The compiler will sort of expand that name out to the full unambiguous name so that the rest of the compiler does not have to worry about like what name is this function and all that kind of shenanigans. And then like pulling out macros too. And so those two steps are kind of like the big thing that separates here from the AST, but also there's some other stuff. So for example, we don't need parentheses anymore because we are making a tree of the like way that your code works, and so you don't need parentheses to disambiguate. It's already in like the canonical structure, so that's gone now. And then also, when we talked about this, like the language gets simpler each time, here doesn't have the concept of for loops, for example, because for loops, if we look at this Rust code here, we have a vector of some values, and then for each element in that vector, we print out that result. This is like kind of what the here would look like if it was written in Rust code instead of the data structure. So you can see that like this for loop calls this into iterator thing to take the vector and iterate over it. So this is like the name resolution part where it's pulling that out. And then we actually don't have a for loop. We have an infinite loop here that does a break whenever the loop is over. So like the here language is more primitive than the full Rust language, but it's able to represent everything equivalently. And this is basically our like first problem. Well, I'll get into that in a second. This is not like why I say sort of about this example is you notice this println macro is still not expanded, and iter.next is like a function that was not expanded. I did that because println expands to like 45 lines of code, and that would just make it impossible to understand, but like in the actual here it would be expanded out. And you can get this a totally different -z unpretty equals here tree. Rust has a pretty printer that no one uses because we have a better one called Rust format that actually does good pretty printing. But it's sort of legacy in the compiler. And so the expanded ones got named unpretty because the output is generally pretty gross. And so this is like a totally separate thing to print out the here tree. And here is that function in the actual like here data structure. So there's an item, and it's got this particular ID. And so we have a node that's an fn up there, which is a function. It's a function declaration. It has this type of the input and this type for the output. And like, is it an unsafe function? Is it a const function? Is it an async function? What's the ABI of this function? All this kind of information the compiler figures out. And this is like significantly easier to manipulate than that, you know, AST structure because it has a lot of this information kind of built in already. And so this is what this here looks like. And here is important because currently in the compiler, almost all of the like passes, like type checking and all that stuff happens on the here. And that's also because mir, the next level down, is newer, so not a lot of stuff has moved over to it. But like historically speaking, here was the only thing that existed. So all the passes are written on here, and we're sort of moving some of them to mir. And so a compiler pass, if you're not familiar with this, is like a way to take the same IR and produce like a different one. So like type checking, for example, would take in a set of here as an input and check that all the types are correct, and then, you know, output that here. Type checking may just say true or false, but like the passes that simplify the loops down, you know, all that stuff kind of like produces here. So you can kind of think of these as just like functions that operate on these different things. And like a lowering step would be like a function that takes in the AST and produces the here, and a compiler pass would be something that takes in here and produces here, etc. Okay, so mir. Mir is the next level down, and the big difference between mir and here is that mir is built around a control flow graph, not around the way that your code is actually written. And this is because several of the checks that rustc does depends on the control flow of your examples, and so these are like easier to do on something that's oriented around control flow. Here's a bunch of garbage of what mir looks like in text. I put these here as interesting. One of the reasons I picked this example is because in debug and not debug, it ends up looking differently. So Rust checks that your numbers don't overflow in debug mode. So you have all this garbage about like checked add and assertions and stuff. But in release mode, it just like adds the numbers and doesn't worry about it. And this still matters because some errors are produced in Mir. The borrow checker, one of Rust's most famous features, is done on Mir, or at least will be as of the 6th of December. So we're like a little bit early, but like in the very near future, it will be done on here, or done on Mir. And so we still need to worry about errors at this step. And then finally, LLVM-IR. This is the format LLVM wants. This is the text output of that, and so there's a bunch of this shenanigans. You can still see this like debugging stuff and add with overflow. Although it's signed add, which is called sad, which I've always thought is funny. It's the same thing with Mir. Like Mir has this concept of basic block, which is like BB0, and so I was thinking it's like sweet talking your code. It's like, hey baby. Yeah, LLVM.sad with overflow, and in release mode, we don't do any of that. We just add the numbers together. But what's important about the difference here is like once we get to the LLVM-IR, we've passed all of Rust's compiler checks. So each of those previous steps had to maintain the information to make good errors. But like once we're ready to generate code, we're not producing errors to the person anymore. Hopefully, LLVM can also like just blow up, especially when you compile LLVM's assertions in, and those are pretty garbage error messages because they don't maintain this information that we need. But like once we get to this step, we're kind of done checking out errors, so it doesn't matter anymore. So none of this has error information sort of in it. Okay, and that's kind of like getting back to like the reason I explain this stuff to you and is like lowering is inherently a problem for giving good compiler error messages, because if we're discarding information at each step and like the checks happen the whole way down this like 3 levels of obscuring information, then how are you supposed to produce a reasonable error message at the point where you've boiled away like almost the entire language, right? And so this is like kind of one of the fundamental problems with giving good errors in a compiler. And so the answer is this, at least in rustc, is this thing called a span. And a span is like incredibly simple, but really powerful. And there's sort of 2 things that make up a span. One is the thing that's literally called span, that's just a wrapper for a 32-bit number. And then the other thing is a span data, which has a low byte position and a high byte position and some sort of reference to the syntax context. And so like, why are these 2 different structures? Well, it turns out that when you're saying that like, okay, from position 0 to position 3 in this particular bit of source code, there's a lot of like position 0 to position 3, so you end up with a lot of these duplicate structures. Since these are talking about like line numbers and positions, you'll end up with a lot of them that are duplicated. And so there's this strategy called interning that compilers tend to take a lot of advantage of. And maybe you've done string interning on like a separate kind of project. Basically what it boils down to is it lets you deduplicate these things. So there's a thing called like a span map that has like a span ID and gives you the literal span. And that ID is this 32-bit number. So the actual data structures hold this sort of like ID number, and they go and fetch the span out of it. And it turns out that like looking that up in the hash map is actually cheaper and uses less memory than storing like zillions of duplicated spans, especially when you're compiling like large amounts of source code. Like the biggest Rust projects that exist are like right around the 1 million line of code base. And so when you're processing 1 million lines of code, you may have like multiple millions of these spans. And so a lot of them are probably going to be duplicated. And so interning is kind of a classic technique to handle these things. And speaking of like this whole context and saving and loading these things, the way the compiler actually does all these steps is through this package called rustc driver. And it's what like drives the compilation process along. The Rust compiler is actually split up into lots of little packages. I mean, lots is like 10, which is still for a compiler a lot. But it sort of looks like this. This is the type signature, and then this is the actual body of the code. What's funny is that when you're working on like what's effectively a legacy code base, we've been stable in Rust for 3 years, but the compiler is like 6 years older than that. And so when you write a compiler that's changing the language that it's written in every day, you accumulate a lot of technical debt. So, so we've been cleaning up the compiler over the last couple of years, but what's funny is like even this giant type signature is not actually formatted according to our formatting guidelines, which does not align these things anymore and uses block indent, whatever, it doesn't matter. But the point is it mostly calls out to this run compiler with pool function. So this is the real main function, and it looks like this. And I'm not going to go through all of what this code does, but you know, the important parts are that it takes sort of the input and it runs some shenanigans on those, but then it loads up this thing called the source map from this file loader, and then it builds a session with it. So if you think about like the way a compiler sort of works, it has all these internal data structures that are ready to understand how your code works, and as it processes your code, it kind of fills up those data structures, and then when it does the like analysis, it reads those data structures to determine what happens. So I've heard a lot of the compiler people joke that the compiler is really like a hash map stress test, because like almost all of these data structures are like some sort of ID that maps to some sort of information, and you store those IDs everywhere to keep the storage costs down, but that means you do like a lot of hash map lookups. And you know, this is particular in the Rust compiler, but in a lot of other ones those are true too. So the source map is what connects those spans to the actual source code that you originally talked about. So that high and low byte position, I never actually really explained, inside of the span is pointing to the byte position of the original source code that you had. And so we maintain the position of like where that information is in the original code and pass it the whole way down through everything. So I'm going to back up really slightly because I want to show you it's been secretly hiding here the whole time. So this add has a span of the low byte was byte 39 and the high byte was byte 40 because the plus sign is one single byte. This X identifier later down here would have this particular, or it's up here actually. So the span is low to high because 37 and 38, X is like 1 byte long. When we look at the here has in it, so like the functions, it doesn't have a where clause, so the span is empty, but like the fact that this is public is that pub keyword at the front, so that's from position 0 to position 3 inside the function declaration of like pub, and so that's stored in this here. And then in mir, there's also this particular span, we output it this way, so this particular file at this particular position. But once you get to LVMIR, you notice that this is completely gone. So those spans are kind of like plumbed down through every single layer of the compiler, but they all refer back to that particular bit of source code, and that's stored in this source map. And so after the source map happens, which is down here, it builds this session, and then we get the particular code gen back end, and then do all this shenanigans, and finally like do the compile with all these different parameters. There's a lot going on in the compiler. And so yeah, the session is kind of like that bag of global state of what is happening across these invocations. So how do we actually produce these errors? Well, there's this rustc errors package that defines all the stuff you need to generate errors. And so there's sort of two big APIs here. The first one is called span error, and that just says, okay, I have a span, please produce an error at that span, and you're done. But the sort of oddly named struct span error returns a diagnostic builder instead that lets you do fancier stuff. I don't know why it doesn't say diagnostic builder in the function name. Again, legacy code, sometimes you don't get to pick the names, but it's returning a builder, which is a struct, so I guess that's why it's called struct span error, but I still think this name is terrible. And so here's an example of that sort of in use. So here we have our session from the compiler, and then we call struct span error on it, and we pass it a span and some sort of initial message, and that gives us this error thing, which is a diagnostic builder. And so what we can do with that is we can say like, okay, from the source map, can we get the snippet of code that this span refers to? And if we can, then we can generate like a nicer error message. And if we weren't, we can sort of generate a crappier error message. We've built these APIs so that like the people who are writing the compiler like passes don't need to worry about all that fancy generation of all the output. All that stuff happens inside this API, and they're just able to say, please produce an error at this point, and then like some totally separate code handles all that printing shenanigans. And so this means it's much easier for the people that are like working on the compiler to worry about it, because good APIs are nice to use. And then finally there's this emit. So like once you're done building up your particular error for whatever reason, you call emit on it, and then that actually like spits out the error. And it doesn't actually stop compilation because you don't necessarily want to die after the first error. Sometimes you do, sometimes you don't. But this is sort of the thing that's like, hey, this is actually an error for real, and not just generating one. So this API, like I've been talking about in the context of compiler errors, but there's actually a little bit more than just strictly speaking errors, because there's a gradient of error handling in any sort of application, and compilers are no different. And so adding extra context, for example, is really important from a user experience. And like you're trying to get the person not just to understand like why the error happened, but what they can do to actually fix that error, right? Like you don't want just people to be like, oh, your program didn't compile. If it said that and nothing else, you'd be like, how am I supposed to fix this, right? And so the whole point of pointing out like where stuff is to give you the first level of information about how to fix your problem. But if you can give users more information, then it's easier to actually fix things. And so the most basic kind of help that we can give is called help. Very straightforwardly named. So these provide like info but not context. So for example, this code here, dangle, is trying to return a reference to a string, and it's trying to make a new string but return a reference to it. And in Rust, this would be a dangling pointer because the string goes out of scope, but we're turning a reference to it, so we'd be pointing at invalid memory. And so here we could call like span help and pass in the particular span, and then say consider giving it a static lifetime. And what happens here, this gives you this message, help, this contains this, help, consider giving a static lifetime. So like this is connected directly to this particular output. And so this is kind of like very general information about what you want to do with like no context given. Sometimes that's the best that you can do. However, we can also give suggestions. So with the span suggestion API, you can give like the span and then the message, but you can also suggest what you think should be done to replace it. So here we have that code snippet that we generated from the source map earlier. And so we're actually saying like put this word quux before the snippet. And this is a made up example. Quux is not a Rust keyword or something. But like, oh no, this is an error, sad. Help, try using a quux here. Quux sad. And so for more complicated cases, and this is something again about like that whole, from the UX perspective of the person working on the compiler, they just have to write this, and the formatting code will automatically like, oh, this is a simple one, so do a small thing, but if it's a big one, it will actually like print it out as a separate, so it's kind of like a more verbose output for bigger examples, but you're able to generate these suggestions of what you could actually like think that we should do. And that's a little better than just contextual help, is like being able to suggest what happens. However, these errors are also kind of like dangerous, because if you suggest something that's also wrong, like you can get people really off track where they're like, okay, I try that, and that gives you another error that suggests something else that's even more wrong. And so this is like a good thing most of the time, but you have to be pretty confident about it. And then lints. Lints are kind of like errors, but they let you control whether or not they should like actually stop compiling or not. So there's kind of these 4 levels of allow is like the compiler will not even tell you if this happens. Warn will give you a warning. Deny will actually give you a compiler error. And forbid is kind of like a deny that is always a deny. So you can say like, I want this particular lint to be ignored, and so I'm going to override it to the allow setting instead. And so forbid is like a deny that you can never allow. So for example, here's some actual lint code in C. So if you type while true, you really should be using the loop keyword instead. And this is not just a syntactic thing, but the compiler is actually able to understand the difference between an infinite loop versus a non-infinite loop, and it can't know that here, but it will know it's an infinite loop here. And the reason for that is because usually this is not true, this is some sort of expression, blah, blah, blah. It's not a talk about constant evaluation. But like the point is that you should write this code for a variety of reasons. And so here's what like making a lint looks like. This uses a similar API, but I'm also going to show you a little bit about like how you can manipulate this data structure over here. So we make the struct to represent our lint, and we use this macro to do some metadata shenanigans. So this is the name of the lint, and it's a warn by default lint, and this is like the description of what the lint looks like. You can ask the compiler, what are all the lints you know about? And this would be the description for it. And so there's this trait called late lint pass. So here, what this is doing is it says check this particular expression. So it's like if we have the here that represents a while, and we have an expression literal as the expression, and that expression literal is a Boolean value with the value of true. So you can sort of see how this is like meta-programming your code in some way, right? Like it's using this data structure to like read what your code is like. So then spit out this message to say, hey, you should be using a loop. And then we can grab that source map and the span out of the source map to get like where this is happening, and then use the struct span lint to suggest that that happens and emit the actual error. So this is kind of a more realistic example of how you would be manipulating, and this is like a here to here pass that generates this stuff, etc. And then, okay, the last thing about suggestions. I mentioned before you have to be confident about suggestions. This is a more recent addition, so I kind of put it at the end. But if we're really confident that a suggestion is going to be correct, we actually have an API that will say, please just change my code to use this suggestion. And so we have this tool called rustc. So for example, I'm going to scroll down to this bottom part first. So there's this older syntax that's like box foo, but we added a keyword for reasons that I'm not going to get into. So it should be written box dyn foo, and that's a translation we can get right 100% of the time. It's really not complicated to just add the keyword in front of it. And so there's this span suggestion with applicability where you can say this is a machine applicable suggestion. And then there's this tool called rustc that you basically say, hey, cargo fix my code, and it will try to compile your code and then take any machine applicable suggestions and just straight up apply them to your source code. And so this helps not only just because if the compiler is going to give you a good suggestion, you probably should follow it, but also if you're trying to migrate a code base. So one of the things that we're doing is like, we have this code will always work because it's like part of the stability guarantee, but you should really be writing this. So what we do is we have a lint that's set by default to allow, so it doesn't tell you that you've written your code wrong. But when you run cargo fix, it sets that lint to warn and then takes the machine applicability into account. So if you want to say upgrade old code to like a newer style, we can actually give you the way to just do that by running a command instead, which is really cool because again, there's big projects like 1 million lines of code, and you don't want to have to like update everything by hand, especially when the compiler is able to like fix it for you. And so this is also from like a user's perspective, the experience here is like much better because it's not like here's 1,000 warnings, go fix them all by hand. It's like here's 1,000 warnings, and by the way, I fixed your code for you. And so we only do that for the ones that we're really sure are actually applicable, but that's like kind of the art of handling this stuff. But that's also something that's really, really important. Okay, so that is sort of the overview of how rustc does these errors and like why we do them and some more details. The big sort of takeaways I want to give you is that like your users will really love you if you care about user experience because it's their experience, they're the users. And with compilers, this span technique is really useful for being able to produce errors and also developing APIs to just like take a span and produce an error message. And then also, if you're writing any sort of like lint tool or anything like that, consider adding a fix-up tool and being able to machine apply those lints because that can really, really help people out. All right, so thank you so much.